Section 2 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 2. The Evolution of Astronomical Methods of Observation. Part 1. The history of astronomical observation is the history of man's attempt to bring the stars nearer to him. His own senses are so feeble and so very subject to error that he has been constrained to devise subtle artificial senses which take the place of eyes and hands. Thus, early he invented position finders, which enabled him to determine with more or less precision a star's direction or position at a given time, and not merely to guess at their position; great eyes, called telescopes, that see what his eyes can never see, and also determine positions with greater accuracy; wonderful spectroscopes, that analyze a star's composition as nicely as if it were a stone picked up in the road; and photographic devices that reveal secrets of star structure that otherwise would never be disclosed by his unaided senses. For determining the position of the heavenly bodies the instruments used have always been comparatively simple. All are based on certain rudimentary geometric principles. As geometry was a science fairly well developed among the ancients, it is not difficult to realize that they had various means of measuring angles, both vertical and horizontal. In most ancient cases, however, the observers have failed to hand down their methods, merely recording the results without indicating the circumstances in which they were obtained, so that it is impossible to discuss the values of the observations and correct them in the light of recent discoveries. It is evident that the instruments of the ancients were simple, but their precise nature is altogether uncertain. The earliest astronomical observations of which there is record were made by the Chinese. The Shu King, the oldest known scientific work, states that 2000 years before the present era the Chinese determined the seasons, that is to say, the positions of the sun at the equinoxes and solstices, by means of 4 stars which have since been identified and found to be so suitable that a modern astronomer could not have made a better choice. The Chinese also determined, 1100 years before the present era, the obliquity of the ecliptic, which they found equal to 23 degrees 54 minutes. The obliquity, which varies, is now 23 degrees 37 minutes, and calculation shows that at the epoch of the Chinese observations it must have been 23 degrees 51 minutes. Hence the error of the Chinese determination was only 3 minutes of arc. Among the few astronomical values which have remained constant during the history of man are the times of revolution of the planets. The Hindus determined the revolution of Mercury with an error of 4/10,000 of a day. For Venus the error was 25/10,000 of a day, for Mars 3/1000 of a day. In the case of Jupiter the error amounts to 1/4 of a day, but it is to be remembered that the period of revolution of this planet exceeds 11 years, so that the same observer could not observe many returns of the planet to the same point of its orbit. This comment applies with still greater force to Saturn, the revolution of which occupies 29 years. Hence it is not astonishing that in this case the Hindus were 6 days in error. Among the ancient Greeks is a measurement of a terrestrial meridian made about 200 B.C. by Eratosthenes (276 B.C. to 195 or 196 B.C.), who found the circumference of the Earth equal to 250,000 stadia, by measuring the angular distance of the Sun from the zenith at the summer solstice, both at Alexandria and at Syene in Upper Egypt, by means of the length of shadow cast by a vertical pillar at noon at each place. According to the researches of Tannery, the stadium as an astronomical unit equals 157.5 meters, 516.7 feet, which gives for the Earth's circumference a length of 39,690 kilometers, 24,662 miles, instead of 40,000 kilometers, 24,855 miles, as we know it. Here the precision is remarkable, especially when it is remembered that the measurement was effected by counting the paces contained in an arc of the meridian and by multiplying the number so found by the length of a pace. The instruments most frequently employed by early astronomers were divided circles and compasses with simple sights, which allowed the line of vision to be directed to the star under observation and its direction as compared with some other line of sight to be measured. Ptolemy's ring or astrolabe, for example, described in the 5th book of his Almagest and used to identify the relative positions of the stars and planets, was composed of two concentric vertical circles. The outer circle, about 16 inches in diameter, was fixed and graduated. It supported the interior ring, which was movable, and carried the two sights. There was also a geometric square, which was used in a manner analogous to that of a table of logarithms. Various forms of apparatus for the measurement of horizontal and vertical angles were early developed, and as the study of the heavenly bodies developed to a point where it was useful in navigation, the cross staff or back staff was invented, consisting of simple sighting bars with cross pieces, suitable for the calculation and measurement of such angles as the heights of the heavenly bodies above the horizon and their distance from one another. Quadrants of one form or another, with a sighting bar and divided circular scale, and astrolabes or celestial circles, also for the direct measurements of angles, were employed. Many of these, by the Middle Ages, were examples of accuracy of division. A quadrant designed by Tycho Brahe (1546–1601), for example, was of 19 feet radius and had its circumference graduated to single minutes. Various forms of armillary spheres were constructed, in which the stars were placed in their relative positions on great circles of the celestial sphere. Such devices served for much of the early astronomical work, taking the place of modern star charts. Tycho Brahe, like his predecessors, employed wooden instruments. One of these was a large Ptolemy's ring, surmounted by a post carrying horizontal arms, by which it was turned in bearings like a capstan, so that the ring could be brought into any vertical plane. Tycho Brahe also constructed a mural circle, by means of which vertical angles could be measured. Hence it was by using the naked eye and rudimentary instruments that he accumulated observations of such precision that they served Kepler as the basis of the researches which led to the discovery of the laws of planetary movement. The eye can distinguish an object whose diameter is equal to about 1/3000 of its distance, which corresponds with an angular diameter of about 1 minute of arc. This was the measure of the precision of early observations. Its value may be appreciated by stating that it corresponds with the diameter of a lead pencil seen at a distance of 70 feet. The telescope, by increasing the distance at which objects can be distinguished, therefore has been and is now the chief reliance of the astronomer in determining position. While the naked eye today may be said to have been very largely supplanted by spectroscopic and photographic observation, yet the telescope has constantly met the demands of astronomers as its power has increased and its scope widened. By chance or otherwise, it was found by a Dutch spectacle maker, Lippershey, about 1608, that two lenses, when placed at some distance apart, would act to magnify distant objects, just as a single lens would enlarge the image of a nearby object. This action of the lens can be explained by considering the effect on a prism of transparent material placed in the path of a beam of light. When a beam of light falls on one of the angular faces of the prism at a direction other than perpendicular to the face, it is forced to change its direction on account of refraction, due to the change in medium. That is, a ray of light passing obliquely through air into a denser medium, such as glass, is bent toward the perpendicular, and in passing out from a denser to a rarer medium is bent away from the perpendicular. A lens may be considered as a collection of prisms of constantly changing angles, so that the effect would be to bend parallel rays coming from a point at infinite distance in such a way that they would all be brought to a single point known as the focus. Consequently, a telescope may be regarded as a light gatherer. The importance to astronomy of Lippershey's invention can be appreciated from the fact that as soon as Galileo heard of it, he constructed such an instrument which, hardly the size of a small toy spyglass, magnified 3 times, or brought the heavenly bodies 3 times as near. He applied it to celestial observation in 1609. The value of the telescope as an astronomical instrument became apparent immediately. It was from the use of his optic tube, as he called it, that Galileo arrived at the conclusion that Ptolemy was wrong and Copernicus right. How will become apparent from a consideration of the discoveries made by Galileo. He did more than this, however, for by the application of the telescope to the observation of the stars, he became in truth the founder of our modern science of astrophysics. Galileo saw hosts of stars never before revealed to the unaided eye. The 6 stars in the Pleiades now appeared as 36, and various nebulous objects of light, such as the Milky Way, were found to consist of multitudes of fine stars clustered together. But his crowning achievement occurred on January 7, 1610, when in turning his telescope toward Jupiter he discovered 4 satellites of that planet, and determined that their periods of revolution around Jupiter ranged from about 42 hours to 17 days. Here was a miniature system similar to that conceived by Copernicus. Was it any wonder that Galileo abandoned the Ptolemaic teaching? Thus Galileo was able to strike a serious blow at the infallibility of Aristotle and Ptolemy, by whom no mention had been made of the existence of such extra bodies. At this time, however, others besides Galileo were working with the telescope, among them Thomas Harriot, 1560 through 1621, in England, Simon Marius, 1570 through 1624, and Christopher Scheiner, 1575 through 1650, in Germany. Thenceforth observational astronomy with the telescope was anchored on a firm basis. As was quite natural, telescopes eventually formed an important part of the equipment of the observatory of Tycho Brahe and of John Kepler, 1571 through 1630. In one of Kepler's works on optics is contained a suggestion for the use of a convex lens for an eyepiece in the construction of the telescope. Galileo's instrument consisted of a lead tube containing a large double convex lens, which served as an objective, and a small double concave lens at the eye end, in order to give an erect image, an arrangement which finds its counterpart in the modern opera glass. Kepler's suggested improvement provided a more efficient and fairly modern astronomical telescope. The actual construction of an instrument of this type, however, is credited to Scheiner rather than Kepler, who was notably deficient in mechanical skill. After considerable experimenting by various astronomers and instrument makers, it was found that a comparatively small objective with a considerable focal length was more useful and effective. In 1672, Cappani of Bologna constructed an instrument of this kind 136 feet long, while Auzout actually made a telescope 600 feet in length, which, however, failed to work. These, of course, were skeleton structures not mounted in tubes. Perhaps the best of them were those of Huygens (1629 1695), whose skill in grinding lenses stood him in such good stead that he was able to construct a telescope with which he determined the ring of Saturn. Huygens' telescope had considerable focal length. He placed the object glass on a tall vertical pole or staff, so balanced that it could be moved in any direction by means of a cord. The observer on the surface of the Earth was supplied with an eyepiece, which he maintained in a straight line with the star he was observing by means of a cord. All these telescopes were refractors. They were subject to certain inherent defects, chief among which was the difficulty of bringing to a single focus all the rays of different colors. The 17th century philosophers believed it impossible to overcome the unequal refrangibility of the different colored rays of light which produced chromatic aberration, and resulted in an image indistinct for the blurring of various colors. Accordingly, they gave up the idea of perfecting the refracting telescope, and directed their attention to constructing an instrument on a different principle, using a concave mirror to form the image of the object observed. Mersenne, in 1639, suggested the employment of a spherical mirror, but the idea appears to have been dropped. Quite independently, James Gregory, in 1663, proposed a similar arrangement, using, however, a parabolic in place of a spherical mirror. At that time he could not find a workman able to construct such a mirror. In the Gregorian instruments the parabolic reflector is placed at the lower end of the tube, while on its axis and a short distance beyond its focus is placed a small concave reflector. The light from the distant object falls upon the large mirror, from which it is reflected back to the small one, which throws it back through a hole in the center of the large reflector. It then passes into the eyepiece, which, indeed, in Gregory's time had been much improved by Huygens. Gregory's efforts turned Newton's attention to reflecting telescopes. In 1669 he cast his first disc and began to grind it, but it was not until 1672 that he had real success. Then he made two small instruments, one of which was only about an inch in diameter, with a magnifying power of about 38. The principle of Newton's telescope differed from that of Gregory's in that it had a small plane mirror placed in the cone of light from the reflector at an angle of 45 degrees. Being placed inside the focus, this mirror brought the light cone at right angles to its original direction, thus forming the image outside the tube and obviating the necessity of a hole in the parabolic reflector. About the same time that Newton completed his instrument, the Cassegrain construction was proposed, which was similar in construction to the Gregorian telescope, except for the small mirror. In the Gregorian this mirror was concave. Cassegrain (1672) proposed the use of a concave mirror inside the focus. It brought the light from the object to a focus through a hole in the center of the large parabolic mirror. Owing to the difficulty in obtaining a suitable mirror alloy, little progress was made for some time in constructing reflecting telescopes. In 1718, however, Hadley, the inventor of the sextant, constructed one on the Newtonian principle, 5 feet in length. The instrument magnified over 200 times and revealed as much as the old refracting telescopes. Perfect as this Newtonian telescope seemed to be, the Gregorian type held the field until 1774. End of section 2.